Hello, this is the Section 4.3 lesson. In Section 4.2 we introduced some of the basic ideas and concepts related to probability. In Section 4.3 we're going to see one formula that's going to allow us to calculate certain types of probabilities. So to illustrate the ideas, we're going to use this table of data. This table represents results from a marijuana drug test. 300 people were given the test. 143 of them tested positive, 157 tested negative. At the same time, they were asked, have you used marijuana or not used marijuana? A total of 122 people said they have used it, and 178 said they have not used it. Looking through the center of the table, we see that 119 people tested positive and used, 24 tested positive but have not used, 3 tested negative but have used, and 154 tested negative and have not used. So what we have going on here is really two different procedures, the test and the question. They're both procedures because we don't know exactly what's going to happen until we give the test to the person and ask them the question. Each of the 300 people is a trial, and each procedure has two different outcomes. For the test, either positive or negative. For the question, they have either used or not used marijuana. So let's consider the procedure of randomly choosing one person from this total of 300. Find the probability that the person tested positive. Well, using Rule 1 that we saw in Section 4.2 to calculate the probability of this event, we take the number of times the event occurred divided by the total number of trials. Well, we have 300 total trials. Out of those, a total of 143 people tested positive, so that's the number of times the event occurred. Thus, the probability the person tested positive is 143 divided by 300, or 0.477. So in practical terms, that means that 47.7% of the people in this experiment tested positive. Well, now let's consider the same procedure again. We randomly choose one person. But let's find the probability the person tested positive or used marijuana. Well, in order to figure out this probability, we're going to search through the center of the table and find the total number of people who tested positive or used. So we're going to start with the 119 up in the upper left-hand corner. Those people tested positive and used, so we're going to count them. The 24 right next to them, they also tested positive, so we're going to count them. The 3 there in the second row, they used marijuana, so we're going to count them. 154 next to them, they tested negative and did not use, so we're not going to count them. So we're going to add the 119 plus the 24 plus the 3. That gives us a total of 146 people who tested positive or used, divided by the total number of trials, which is still 300. And we get our probability there of 0.487. So in practical terms, that means that 48.7% of these people tested positive or used. Well, a third example, let's consider the same procedure again of randomly choosing one person, but let's find the probability that the person tested positive and used marijuana. So again, we're going to look through the center of the table, count the total number of people who tested negative and used, divide that by 300. Well, looking through the center, we see that only 3 people both tested negative and used, so that's our numerator. Our denominator is still 300, so there's our probability of 0.01. So in practical terms, that means that 1% of the 300 people tested negative and used. Well, let's look at a caution here, a mistake that we might make in trying to calculate these probabilities. Again, same procedure, we randomly choose one person, find the probability the person tested positive or used marijuana. Well, I might be tempted to simply look at the right-hand column and the bottom row of the totals and say, well, a total of 143 people tested positive and 122 people used marijuana. So let's add those numbers, 143 plus 122, and then divide that by 300, and we get 0.883. Notice that's quite a bit higher than what we got doing the calculation the correct way. Well, what's wrong in this calculation is that we simply double counted the 119 people who tested positive and used. If you notice the 143, that's the 119 plus 24. The 122 number, that's the 119 plus 3. So if we add the 143 and the 122, we've double counted those 119. And we don't want to do that. So this caution illustrates the basic idea behind what we call the addition rule. The addition rule is a rule for calculating the probability that one event or a second event occurs in a single trial of a procedure. So to find the probability of A or B, find the sum of the number of ways event A can occur and the number of ways event B can occur, adding in such a way that every outcome is counted only once. And that's the key phrase there, only once. A probability of A or B is equal to that sum divided by the total number of outcomes in the sample space. So the idea here is pretty simple. Count the number of ways the events can occur, but make sure you count only once. Divide that by the total number of outcomes in the sample space, and you have your probability. Now, in formal terms, we'd write this as P of A or B. A or B means that one event or the second event occurs. That equals the P of A plus P of B minus probability that A and B both occur at the same time. And we have to subtract there to make sure we don't double count anything. If we don't subtract, then we could double count things. Now, there's a certain case where we don't have to worry about double counting, and that happens when we say events are disjoint. So events A and B are disjoint, or what the book calls mutually exclusive, if they cannot occur at the same time. So they're disjoint if they cannot occur at the same time. So let's look at some examples from our drug test here and determine if they're disjoint. So let's take the first event to be the event that they used, and the second event to be the event that they tested negative. Well, if I look there at my table, I see that 3 people used marijuana and tested negative at the same time. So they can occur at the same time. That means they are not disjoint. Let's look at another pair of events, not used and positive. Well, we see that 24 people tested positive and did not use marijuana at the same time. So they can occur at the same time, thus they are not disjoint. Let's look at the third pair of events, tested positive and testing negative. Well, you can't test positive and negative at the same time. You're either going to get one or the other. So those cannot occur at the same time. So those two events are indeed disjoint. Let's look at a couple of other examples. These don't have anything to do with the this marijuana drug test. But let's consider the procedure of randomly choosing a car from a parking lot. So let event A be the event that the car has a dented fender, and B, the car has a flat tire. Are they disjoint? Well, we've got to ask ourselves, is it possible for these to occur at the same time? So is it possible for a car to have a dented fender and a flat tire at the same time? The answer is yes. So they are not disjoint because they can occur at the same time. Another procedure, say we purchase a new shirt. Event A be the event that the shirt is free of defects, meaning that there's nothing wrong with it. And the second event, the shirt is missing a button. Are they disjoint? Well, if it's free of defects, then it can't be missing a button, because missing a button is a defect. So these two events cannot occur at the same time, so they are indeed disjoint. Now, disjoint events have a very special property. If A and B are disjoint, then the probability that A and B occur at the same time is equal to 0. Now, hopefully this makes intuitive sense, because if they are disjoint, that means they cannot occur at the same time. The probability of something that cannot occur is 0, just by definition. Now, this is special because in the case of disjoint events, our addition rule is simplified. Here's in the first line is our original addition rule. P of A or B is PA plus BB minus P of A and B. Well, if they're disjoint, then P of A and B is 0. If we subtract 0, it doesn't change anything. And so our formula simplifies down to P of A or B is equal to PA plus PB. We don't have to subtract because if they're disjoint, we don't have to worry about double counting, and our formula simplifies down to something that's very easy to use. So let's look at one very simple example of using this formula to calculate the probability that one event or a second event occurs when they're disjoint. So when we roll a fair six-sided die, the probability that we get a number less than 3 is equal to 1/3, and the probability that we get more than a 4 is also equal to 1/3. Well, getting less than a 3 and more than a 4, those are two different events. They are disjoint because it's impossible to get less than a 3 and more than a 4 at the same time. So if I wanted to calculate the probability of less than a 3 or more than a 4, I could use this simplified formula to say, well, that's equal to the probability of less than a 3 plus more than a 4. I don't have to subtract anything because they're disjoint, and I don't have to worry about double counting. Okay? Well, now these two probabilities we know are both 1/3. 1/3 plus 1/3 is 2/3. So there I've calculated the probabilities. That's it for section 4.3. The homework is posted on Course Compass.